participants. I welcome you to this very excellent class where we're going to be looking at the per unit value in power system engineering. Before now, you have been introduced to the representation of power system in terms of the network, where we showed you the single line representation, the impedance diagram representation, the reactance diagram representation. All of these are actually done to simplify the entire power system and help us easily analyze the power system. Of course, we are also going to be looking at here the per unit value. Here we are going to be looking at the respective quantities of each element in the power system. Now, those elements which include, as we have shown before now, the transformer, the generators, the load, all of these components. Now, each of them have their quantities in terms of their voltage, in terms of the power, in terms of their impedance. So we are going to look at also how these quantities can be simplified. And also in per unit here, we are going to be seeing how a transformer can be replaced with the reactance, thereby reducing the entire circuit to a simple single line circuit without transformers here and there, thereby simplifying our analysis of the circuit. So now let's get into class and look at the per unit value. Now, mathematically, the per unit value of any quantity can be defined as the ratio of the actual value in any unit to base value in the same unit as the actual value. What do we mean here? We consider, for instance, if we talk about the per unit value of power, it is going to be the actual power, which we abbreviate as SE, all over what? The base power, which we abbreviate as SB. And each of them must be in the same unit, either in kilowatts. Two of them must be in kilowatts, either actual power in kilowatts, all over base power in kilowatts, or actual power in kVA, all over base power in kVA. They must actually be in the same unit. Then we are also looking at, we consider voltage in per unit. How do you represent voltage in per unit? We are also considering the actual voltage VA all over the base voltage VB. So what about per unit current? The same reason. Actual current all over what? The base current. What about per unit impedance? Actual impedance all over base impedance. Now, if we look at this, it is very important for you to note here. If we are considering, take for instance the actual current, you know current is measured in amps. Then it then means the actual value will be in amps and the base value will also be in amps. So you see, if we are comparing these two, the ampere units will cancel themselves, and when they cancel themselves, we'll be left with no unit. That is to say that per unit value actually has no unit. The unit of per unit value is actually per unit. So we represent it with per unit, not with amperes, not with impedance, not with resistance. Be it resistance, you just say the unit is per unit, but it will be indicated that this is resistance in per unit. So you just know that it's a per unit value, that it was compared with a base value. So this is the value of that resistance or impedance at a given when compared to a determined or a given base. Now, choosing your base values. For the purpose of our analysis, which we have said here is the power systems analysis or power systems engineering. Here we are considering, we have generators, you have transformers, and the rest of that, which form up the power system. Now, how do we choose our base? Of course, we have the S base, which is the apparent power. We choose the apparent power, we take the apparent power, which will be a common power for the entire network that we are considering, or the entire power system. Then also we choose the base voltage. So what is this base voltage? This base voltage is the voltage, say for instance it can be the voltage of the biggest generator or the highest voltage in the system. Yes, also for the purpose of the power can be the highest generator, the power rating of the biggest generator in the power system you want to analyze. This is actually the rule of thumb. That is, I am saying, if you are not giving the base power, you are not giving the base voltage, this is how to decide what to take as your base power and what to take as your base voltage. Now, like we have registered here, you see the base voltage can always vary in the power system, because while the power remains don't change, it doesn't increase or decrease, but the base voltage continues to vary. And why does it vary? Because we have transformers in the power system. The voltage into a transformer is different from the voltage out of the transformer. Take for instance, if we are talking about step up or step down transformers. So you see, if for instance we choose a voltage of say 200 volts, and we are considering a transformer that has a turns ratio of 1:2. That is, the primary is 1, the secondary is 2. So you can see that if we choose a base voltage of 200 on the primary side, the base voltage will change on the secondary side to what? To 400, because we are considering 1:2. But if we are considering maybe a transformer that is 2:1, you see, if we choose the base voltage of 200 on the primary, on the secondary it is going to be 100 volts. So you can see with the transformer the base voltage continues to vary. Now all other components, now because when we are talking about the power, various components, we are looking at their voltages, we are looking at their powers. What about their impedance? What about the current? How can we get to find the base current, base impedance? Of course, we know when we have the base power and you have the base voltage, you really can determine all other parameters using the normal electrical laws that are actually known to us. You can find a relationship between the base power and actually the base voltage, and with that relationship we can determine the base impedance, we can determine the base current. Now let's look at that. Now you can see using this table, for instance, if we want to find our base current, already we know our base power. This is our base power all over what? The base voltage. This will give you the base current. Now what about for a three-phase system? Because it's a single phase system. For a three-phase system, this is a three-phase power actually all over what? V line to line base multiplied by root 3. You can get the base current, I phase. Then what about the base impedance? That is the Z phase. We can achieve this by actually using this relationship V squared all over per phase power. Then what about for a three-phase system? We have it to be VL base over three-phase power. So we can see that you can prove this formula, considering the relationship between impedance and power. How you can find impedance when you are given the power and you are given the voltage. So now we want to consider another scenario, because what we considered is how to determine per unit values actually through a very straight means. For situations where you are given the actual values and the base value, we can find the per unit. Now I want to look at a situation where you don't have the actual value of a particular component of the power system, but then you have the per unit value. And then when you consider also the base power at which that per unit value was given to you is different from the actual base you chose for your calculation, because before you go into your calculation you choose a convenient base. Like we say, sometimes for the rule of thumb you can choose the power of the highest generating equipment in the power system. Now let's take for instance, there are other generators in the power system that are smaller. Their power will not be equivalent to that. So you see that if you have their per unit impedance, is the power at which that per unit was actually formed is different from the actual power which you have chosen as your base power. So what are you going to do? You are going to convert this per unit value to capture in the new base power. And how can we achieve that? It's simple. That is what we are showing you. So if you follow this arrow here, you will see that we already know that the per unit value is equals to what? The actual value all over what? The base impedance. So from that we can say that the actual value can be determined by what? Multiplying the per unit value times the old base. Can you see that? So now we'll say, what about the new per unit value? The new per unit value is also given as what? The actual per unit impedance all over what? The base per unit impedance. Now what about the per unit impedance, the new per unit impedance? Can we also do something here? We say this will be equal to now this actual, which is the same thing as this, because yes, we are looking for the per unit impedance of that particular component of power system again in our new base. So you can see it, we just have it there to be the actual impedance all over what? Impedance in our new base, which is going to be that. So then we'll have a substitution for this, which is this old per unit value multiplied by what? The old base, which is actually given for that particular component. So you just come here and substitute that. Instead of ZA, we now put Z1 times that divided by the Z base new. So already we know this will be, finally, this is Z1 times, then we know actually the formula for calculating our base impedance. Like I told you, you have the base power and you have the base voltage. So our old base will be given as V squared base old base all over what? The SB base old. So this we have it also divided by, in place of Z base new, we substitute the V squared base new all over S base new, and you can see that that's what we have. So if you do your mathematical analysis, you know this will come up and become inverse. This will be multiplied by the inverse of this. The inverse of this will become SB all over what? VB new squared. So you see that? So when you do your calculation, you see it will come this way. So what we just did here to simplify, this formula will be used to now calculate the new per unit value in the new base, knowing the old per unit value, which is Z1. So now, to analyze a power system containing a transformer, the following should be noted, and that is to say the base parameter for power is applicable for both sides of the transformer, since the transformer ratio does not affect the power through it. We have actually maintained this, that the power can be chosen for the entire power system. The power is not affected by the transformer, the power remains constant throughout the system. But then the second point here, which is the voltage, we can see, like I've explained earlier, that the voltage would always change in terms of the turns ratio of the transformer. We have explained that. You can read that up. Then we have the transformer impedance in ohm referred to the primary winding is not equal to that referred to the secondary winding, which is true. We have, as a result, the analysis involving transformer is complicated, since it has to be done by referring all parameters to either side of the transformer. However, in per unit representation, this is one of the beauty of per unit representation. We have that the equivalent impedance values are the same at both sides of the transformer. Now what we are trying to say, in transformers, in the per unit representation, we have that the equivalent impedance, that is to say the per unit impedance in the primary side, when you refer the impedances to the primary side, or the per unit impedance when you refer the impedances to the secondary side, they are the same and the same value. We are going to see that in an example we are going to be showing you, so that you see that whether you refer the impedance to the secondary or refer it to the primary, you see that of course the per unit values remain the same. Let's look at an example. Now look at this example. We have to prove that the per unit representation, the equivalent impedance values are the same at both sides of the transformer. How do we show this? Now let us consider a two-winding transformer. Look at the impedance on the primary, that's the impedance on the secondary. The turns ratio we can take to be 10:20. Fine. We have that the rating of this transformer is what? 100 VA. So you can see we can choose this 10V as also what? the base voltage, while 100 VA is the base power. So we say the reactance solution, the reactance referred to the primary side is, if we want to refer all the reactances to the primary side, you know how that is done, is going to be this multiplied by what? The square of the turns ratio, the transformer turns ratio. So what is this transformer turns ratio? The transformer turns ratio here is 10/20. So you're going to be moving this to this side, so it's going to be multiplied by the square of this. So when you do that, you have, it's going to be, this is equal to 1 plus, yes, this crossing this side would become 10/20 squared, times 2, like I told you, the square of the turns ratio. So this is the turns ratio, and everything will give you 1.5. So now at the end of the day, you're going to have, when we refer the reactance to the primary side of the transformer, we're going to have J 1.5. Now let us consider also when we refer it to the secondary side. Now what if we refer all the impedance now to what? The secondary side of the transformer. How do we do? Now, like the other case, if we are referring to the secondary side, we are going to have the primary side impedance divided by the square. In the other case, we said if you are referring from the secondary to primary, it will multiply. But when you are referring from the primary to the secondary, it will divide. So you can see here we have it, that is going to be 2, which was formerly on the secondary side, plus that 20/10, which is the turns ratio squared, times 1, which was the reactance on the primary side. So when you do that addition there, you're going to have J6. This J here is telling you that is a complex value. Then we have that the final equivalent circuit for this is going to be this. This is the equivalent circuit for all the reactances referred to the secondary side. Then now let us, having found the reactances, the actual reactances when we refer to the secondary and when we refer to the primary, now can we go ahead and look for what? The base reactance. What is the base reactance? Like we told you, just like we have impedance here, the base reactance will also be equivalent to what? The square of the voltage square, all over what? The base power. So we can see it here, towards the base reactance at the primary side. If we want to check for the primary side, we already told you that the voltage on the primary side is 10. You can see that 10, and the secondary side is 20. So what is going to be the base impedance or the base reactance here? The base reactance here will be equal to V squared, that is V squared base, all over what? The base power, which is finally 10 squared all over 100, and that is going to give you. So what about on the secondary side? We know that the voltage has changed, and instead of 10 we are going to be using 20 all over that, and that will give us 4 ohm. So now we have found the base impedances, we have also found the actual impedance. So we are set to get the per unit values on both the primary side and on the secondary side, having found the base impedance and actually determined the actual impedances referred to the secondary and refers to the primary side. So now let's go. Then now when we are considering the primary side, the per unit impedance on the secondary, like we said, is going to be the actual value all over what? The base value. We know that for the primary side, we got our base value to be 1 and actual value to be 1.5. So when we do that, you are going to have 1.5 per unit. Wow, we have found the per unit value for the primary. Now let's confirm for the secondary. Is it going to be the same for the secondary? So let us look at it. So when it's referred to the secondary, you can see that when it's referred to the secondary, finally we say reactance referred to the secondary side is going to be 6 over what? 4. What is this 6? This is the actual value. Remember from our calculation, we got the actual impedance referred to the secondary to be 6. Now this is the base value, which is 4. So when you bring it to this side is 4, and that would be equal to 1.5 per unit. Now can you see, if we try to look at the two of them, we see that whether you refer to the primary or you refer to the secondary, your per unit values will always be the same. So in every calculation you have, you can either refer your reactance to the primary, or you can either refer to the secondary. In whichever side you refer, you don't need to be doing your calculation to and fro again. You just use any one that you have done, your values remain the same. So this is the per unit circuit. This is reactance referred to the secondary side of the transformer. So you can see this is per unit value, which is 1.5 per unit. So you see whichever side you use, so we can replace the circuit now. Instead of having this coil of a transformer, we can just replace the circuit with, we say the input is this, base voltage of 10, base voltage of that, and we can see our per unit voltage, which should be here. Our base voltage used to be 20, and we actually have that the given voltage to is 20, so 20 over 20 will have 1 per unit as the voltage. This side the same thing, we have 10 over 10, which is 1 per unit at the same thing. So this is our per unit reactance. I think this is beautiful. So we'll look at how it works when we look at a bigger problem. Okay, the advantages of the per unit system. Of course, there are things we enjoy with the per unit system, and that's why we are studying it. That's why engineers adapted it. Now, one of the advantages is one, comparability. The per unit system allows for the comparison of electrical quantities across different systems and levels, such as between generators and loads, and between transmission and distribution system. Of course, we are telling you that it helps us to carry out comparison. Now, having chosen our voltages, we begin to compare this voltage with all other components in the power system. We compare the impedances and the rest of that. So you see, it gives us a good sense to compare. Okay, when we see the load voltage finally in terms of the source voltage, we can see that, because when we choose our source, our base value to be the generator voltage, we are comparing that generator voltage with the load voltage, so we can see the difference in our per unit value. So it gives us room to compare quantities. It also simplifies the circuit, like we try to let you know. If we're able to remove the transformer and replace it, like we saw, with just a single straight line and no longer as a coil, so you see we can analyze the circuit as a single straight circuit, current moving from the primary to secondary through a single straight circuit, and no longer going through that coil, and we'll have to be looking at how to transform the current from this side to that side of the circuit. So it reduces that burden of work. So accuracy, of course, since we'll be working with lower values of quantities, errors due to calculations is actually eliminated, because the size and volume of data we're working with finally has been reduced, so reducing the error. Then flexibility, of course, per unit value can be easily adopted at any level, and it is a versatile tool for electrical engineering, so you can apply it anywhere. It just have that unique rule, the actual value over the base value, so it's applicable everywhere. It has no special preferences. Then we have standardization. Now, standardization here talks about, it has become a widely accepted tool. So you can see, if you have paid attention to transformer nameplates, you will see most times that what you have represented on the transformer nameplate is the per unit impedance. So you see on the nameplate, you will just see the per unit impedance of the transformer. Most times even you find it also on generator. So it is now a standard value, so widely adopted and accepted. So that's another beautiful advantage. So in your doing your analysis, you just have the values in per unit. You can do your analysis easily and give your solutions as the case may be. Well, thank you so much for listening, and see you in our next class. Goodbye.